So up next, we have Wang talking about the Electrostatic Dust Analyzer.
Yes, next slide, please. So as we know, dust on the lunar surface is charged by solar wind, plasma, and by solar UV radiation. So then you would think those charged dust may be moved, lofted, or transported by electrostatic forces. So first, evidence of electrostatic dust lofting is this so-called Lunar Horizon Glow. I think everybody knows about it. And it's observed by Surveyor 5, 6, and 7. And it's like less than a meter high bright glow above lunar horizon. And later, next slide, please. During Apollo missions, there's a LEAM experiment deployed on the surface that detected low-speed dust, especially at dawn dusk areas. And also on the right side, it shows asteroid sketch about this showing high altitude horizon glow. And look at the shoulders and also the streamers, high altitude streamers. And also, they argue caused by tiny dust particles lofted by electrostatic force. But also, I like to warn you, there's still controversy. Later work showed contradictory results, as shown on those two pictures. The next, a very recent lunar observation by Chang'e 3 rover. So the rover took images on lunar rocks and analyzed the reflectance. They found there very thin dust layer deposits on rocks up to about 28 centimeters, and which is the similar height to the horizon glow. And they also believe electrostatic dust lofting it could be a mechanism to explain this. The next slide. So beyond the moon, there have been several observations related to electrostatic dust transport. So here are some examples. On the left, there's radio spokes in certain bearing. You see those dark lanes in the highlighted box, and also dust pounding processes on asteroid arrows and also Comet 67P. Just very fine dust deposits in the bottom of craters, and also highly smooth surface of certain acid moon Atlas. So all of those are related to the electrostatic dust. And if it's true, you see that it's a universal phenomenon. So which means it can play a very important role in the surface evolution of airless bodies. This is why we really care about it. Okay, next slide. However, then we run into a problem. A fundamental question is, how do dust particles obtain enough charge to become lofted in the first place? This question has remained for decades for scientists to answer. And until recently, next slide. So we had laboratory breakthroughs in understanding the fundamentals of dust charging and lofting. And on the left, it shows electrostatic loft dust in the laboratory just by turning on a UV lamp or a low energy electron beam. And this is the 20 micron, 40 micron size dust particles get lofted on the Earth's gravity. So we think this is strong evidence. Then we developed the pie chart model to explain that. The key thing is the cavity, the microcavity is formed between dust particles can absorb photoelectrons and secondary electrons, create substantial negative charge on particles and then repel each other to get the dust particle off the surface. After that, I have several follow-up experiments to prove this, and also have much better understanding about those lofting characteristics. Next slide. And so I think the outstanding questions for dust and dust mitigation, first is how does electrostatic dust transport play a role in shaping the surface physical and spectral properties on the surface of the moon and airless bodies? And what are the charging states and behavior of dust particles lofted naturally or by human activity? So that's important for dust mitigation. Next, then we came up with this electrostatic dust analyzer to characterize lunar dust transport. It's like a 20 centimeter cube. It's designed to be deployed on the surface of the moon, but it also can be mounted on the lander. It can be tilted to the large angle range to collect dust, lofty dust falling back. It has symmetric design, so it can allow dust to come in the instrument from either of the ends, depends on the position to the sun. So this is funded by Dolly program and it's currently under development. You see this is the mass is about 5 kilos, it's about 5 watts of power.
4 minutes.
Next slide. So this is how it works. On the left, the scan shows so that a charged dust particle comes through and there are a bunch of wire electrodes. If you look at the right, you can see those wire electrodes, and then charged dust will induce charge on those wires, and then you can measure the induced charge to measure the dust charge. And you have 2 wire electrode planes, and you get time difference from charge signals. Then you can derive the velocity. And then the dust particle will pass through the deflection region, will be deflected, and exits through another charge trajectory sensor. So you can measure the deflection, which gives you the charge to mass ratio. So you have the 3 fundamental parameters: charge, velocity, and mass. All right, next slide. So this is the TRL-4 showing here, developed a couple years ago. Let's demonstrate how it works. And you see the charge signals on the right. And we're going to reach TRL-6 by March 2022 or even earlier. And all right, next slide. Okay, so to conclude, electrostatic dust lofting and transport is this 5-decade-long problem, which has been related to a number of phenomena on the airless bodies. And recent lab experiments made important breakthroughs in understanding the fundamentals and dust charging and lofting, which make us believe this may indeed occur on the surfaces of the moon and asteroids and other airless bodies. So we think this is very fundamental science, which needs in situ measurements to really determine the ground truth of this electrostatic phenomenon. In order to understand the surface evolution of the moon and airless bodies. And also it's important to understand, human caused dust charging and behavior. So I will stop here. I think I have a minute. I can take questions if you have.
Okay, thanks, Shu.